morning, sir, and good morning, everybody else. Today I'll be presenting about my professional development. Okay, so first of all, this is my LinkedIn account. This is me. This is my JobStreet account, my LinkedIn account, and then my BEM account. Okay, so for competency A, I had to design and implement a rectifier which has to convert a 9 volt AC to 5 volt DC. So for this one, the requirements are that I need a 1000 kilo ohms, 1000 ohms load, and then the output voltage ripple of 2%, less than 2%, a rectification efficiency of 75%, and it has to be cost effective and use the least amount of components. So for this, because based on this criteria, I decided to use a half-wave rectifier layout because it uses a lot less component than a full wave one. As you can see, it only uses one diode for the rectifying. Other than that, it's also very cost effective and easy to design. While although using the half-wave one, the input wave is actually only the positive amplitude. I actually use a capacitor to help smooth out the output. So basically this is how it works, the block diagram. From the input source, we have 9 volts at 50 Hz. This is how the sine wave looks like. And then after going through the half-wave rectifier, which is the 1N4001, it will only take in the positive amplitude. Because the rectifier only allows current to go past in a single direction, so it will only take the voltage from the source. Next, it will go through a voltage regulator. For this one, I use a Zener diode, which helps to regulate the maximum voltage at only 5 volts, which is the requirement. Other than that, I also use a capacitor in parallel with the loads to reduce the voltage ripple right here. The capacitor can store the charge and then discharge it, thus smoothing out the voltage output. Okay, so for the component section, why I choose 1N4001? Actually, I had many choices, one of which is 1N4148. At first, I wanted to use it, but then after analyzing the data sheet, actually I found out that the diode here is mainly used for high frequency switching purposes. So I didn't use that one. And then I also wanted to choose a Schottky diode, the 1N5H20, because it has a low forward voltage compared to a normal diode. Normal diode has like 1.1 volt one, but it's very expensive compared to normal diode. So to fulfill the requirement, I just use the 1N4001 diode. Next, to regulate the voltage, I use the Zener diode, right? Well, the Zener diode actually works like only works in reverse biasing mode, as you can see here from the graph. So actually, you can see here, right? My Zener diode is actually placed in the reverse bias placement because this diode works in only after breakdown voltage. So basically, the Zener diode works normally as a normal diode during forward bias. But however, when it's placed in reverse bias, it actually allows current to pass through during the reverse bias. As you can see here, when the current is a reverse current, it will slowly go down here as the reverse voltage. So when it reaches around 5 volts, and here it's only 6 is example. So when it reaches the 5 volts, which is actually the Zener voltage or breakdown voltage, it will start to decrease rapidly and it will stabilize around 5 volts. And basically, yeah, this helps to regulate the voltage at around only at 5 volts. Perfect. Other than that, I also use a very big capacitor, 1700 microfarad capacitor, as to I want to smooth out the ripple voltage as much as possible. Next, for common system B. So basically, I will apply some formula and some engineering knowledge to get the value that I need to properly evaluate my rectifier. So the requirement just now said 2%, right? 2% voltage ripple. So basically, I have to translate the 2% into how much voltage it is. So basically, I assume my output voltage is 5 volt. So basically, 2% of that is 100 millivolts. So my output voltage has to be around less than 100 millivolts. Other than that, I also have to derive the rectification efficiency formula. So normally for rectification efficiency, right, it's the DC power over the AC power. So as you can see here, I substitute DC times I average load, and then DAC times IRMS in. So actually, when we assume that the ripple voltage is less than 100 millivolts, and then the capacitor is fully charged, the current IRMS in here can actually be substituted into I average load, approximately that. So basically, I just did that, and it's in my formula, VDC times I average load over VAC times I average load. By the way, the VAC is VRMS. Okay. So then for the simulation setup, I also use some formulas to automate my calculation for easier analyzation. So I'm using the built-in SPICE directives from the LP-SPICE, and I basically do it like this, and then the output is here. So for example, I wanted to calculate the peak-to-peak voltage of the of the output, right? So basically, I write here the function dot measure. PR is the name of the variable. P2P, PP is the function P2P, and then P out is the source of the source of which I'm calculating it from. So V out is